Hello and welcome to Module 6, Ethernet and the Internet Protocol. So there's a lot of information in this chapter, and I will have a couple of other videos that I want you to look at, especially with the IP subnetting and IPv6 stuff. So there's a lot of content, but hopefully if you did the CCNA 1 course, it should be a quick review. Okay, anyway, so let's try to cover as much as we can with this chapter. So we will cover the Ethernet, which is the wired protocol for most desktop and enterprise networks. The other one is the 802.11, the wireless. But if you are wired, most likely you have an Ethernet network. We'll talk about the IPv4, the IPv4 addressing, just the basics, fundamentals. But again, I have some other videos that I want you to watch from CCNA 1 course. And then we'll talk about the different types of IPv4 addresses. We'll look at the default gateway, what it means, and then we'll review some of IPv6. All right, so let's talk about Ethernet. Ethernet operates at the bottom of the 2 layers of the OSI model. So remember, I'm going to ask you to take some notes, by the way. Okay, so in your computer, when you are encapsulating data, you start at the application layer, the presentation, the session, then you get to the transport, where you take the data up here, and you give it to either TCP or UDP at the transport layer. And what TCP and UDP does is they break up the data into segments and attached on them port numbers. Remember from last week, port numbers identify what type of application were given to you. And the sequence number is also placed on them too, because you split them up into multiple pieces. You want to make sure which one comes first, which one comes second, so that the receiver on the other end is able to reassemble the data back together. So once these segments are done, they are given to the network layer. That's where the IP protocol, either IPv4 or IPv6, will encapsulate these segments that are given to you from the transport layer, either from TCP or UDP, and you place these segments into a packet. Then on the packet, you will place the IP addresses, either IPv4 or IPv6, like I said. You place the source IP address, which is given to you most likely from a DHCP server, and then you're also attached the destination IP address, which most likely is given to you by the DNS server. Once that packet is done, then you give it, this is all software, by the way. We haven't even got to the NIC yet, your network interface card. Then you give it to the data link layer. The data link layer is made up of 2 sub-layers. One is called the logical link control, LLC, and the other one is the MAC. The LLC is the one that communicates with the network layer. He grabs the packet, puts it into a frame, like a little box, and on it will place what type of data that was placed in there. That's all the LLC does. Sets up the frame and puts the data in there and puts a label on it indicating what type of data. Is it IPv4? Is it IPv6? Is it some sort of other type of layer 3 data? It doesn't have to be IP. It could be something else. But that's what the LLC. Then the LLC gives it to the NIC, the Media Access Control sublayer of the data link. So the MAC sublayer and the physical layer is where your network interface card, the hardware, comes into play. So the NIC takes that frame that was done by the LLC, and he puts the MAC addresses. He finishes labeling the frame, puts the source MAC address, which he gets it from the NIC, and places the destination MAC address on it, which most likely he will get it from an ARP request. And once that's done, media access control, meaning he is going to access the media, the physical layer, the wire, if it's because it's Ethernet, he puts it on the wire in bits, in ones and zeros. Okay? So that's basically, we just a quick review of the encapsulation process of how data gets encapsulated and placed on the wire. On the other end, you will, encapsulate the data once you capture it. Okay, here's the frame. So please write this down because I need you to understand. This is very, very important to know. Okay, because this is what you're going to be asked this on the exams and you name it. Anyway, so write these down, and if you can, take a picture of this, the Ethernet frame itself. So let me go over this again. So right here, data this is where the layer 3 packet is, IPv4. So it's placed in here. So the maximum, here's something to remember, the maximum packet size that an Ethernet frame can hold is 1,500 bytes. The minimum is 46. So if the IP protocol at layer 3 gave you a packet that is 46 bytes, you have to pad it, put some zeros next to it to bring it up to 46. Once that's done, right here, this is in the frame, you put a label to indicate, a number, 2-byte number, to indicate what type of data in there or what length, typically what type of data that you placed in there. That's what the LLC does, places the data in there and puts the number in there. He doesn't put anything else in there. Then he gives it to the MAC sublayer. The MAC sublayer looks at the NIC, finds out what the MAC address, places it right here, and doing an ARP request, get the MAC address of the destination who you're going to send it to, and you place it right here. So that's your frame. Before you send it out, you take from here the data all the way to the destination, and you place it in a cyclical redundancy check, like a hash program that looks at all the ones and zeros and comes up with a number and places it right here. This is called the frame check sequence, FCS. This is to check the integrity of the data. This is like taking a picture of exactly how the frame looks and stamping the picture right here. So when you receive it, you take a picture again and compare it to see if it's the same. Otherwise, when you receive the data, you are going to run this through the same hash program, CRC, and then the number that comes out has to be the same as is placed on here, right? And that means that the frame was good. If it's not the same, then the frame is no good. Then you'll ask the destination the source to resend your data. The preamble is really 7 bytes of alternating ones and zeros. That's 56 bytes. And then 1 byte of 0, 6 ones, and a 0. But this is only applicable if you have an old 10 base T, 10 megabyte, megabits per second Ethernet NIC. Okay? So please write these 2 bullet points. That's important. Anything larger than 1,500 bytes are considered to be jumbos. Good. Or anything less than 64 bytes, which is you add 6, 6, 2, 46, and 4, is called a fragment or a runt frame. That's something good to remember for down the road. All right, so here's an explanation of this. Again, take a picture of this. That's good. It's always good to remember these. Okay. All right, so let's look at the MAC address. The MAC address that you get is 48 bits. The 48 bits, how do you get the 48 bits? Because it's unique and no one else in the world will have it. So what you do is the company that makes up the network interface card, they have a serial number according to, it indicates what company they have, 24 bits. So they make up their own 24 bits, and then they call the IEEE, and they give them another 24 bits called the OUI, the Organizational Unit Identifier. Together, they make up the MAC address, and that will be unique. No one NIC will have the same MAC address as other. So they are all going to be different. And this is how they are represented. Each bit is is a hexadecimal number. Again, we'll cover this in other videos. But each of those digits is 4 bits. So it could be written with dashes. So this is 4 and this is 4. So this is an 8-bit number. 8, there's 1, 2, 3, 4, 5, 6 of them. 6 times 8, you get 48 bits. So most likely either see them in this way or with colons. Sometimes on the routers or switches, they are written in hexstats with a dot between them. That means 16 bits. It is very important. Take a picture of this to remember this. So if somebody says, give me the equivalent of an A, it's 101. Give me the equivalent of what's E in binary, 1110. Okay? Again, in the videos and in class, we will review some of this to make sure that you understand. Okay, let's take a look at IPv4. IPv4 is a layer 3 network. It operates at the layer 4. So the network layer is where the routing happens, and routing meaning finding one network to another network. And every network should be network meaning an area, and they are assigned an IP address, like a zip code, if you remember what we talked about. So routers just need to route the data from one area, one network, one subnet, from one zip code to another. So that's what all the routers are for, is just to get your data to the correct area that you are in according to the IP address. The IP address is equivalent to your zip code. Okay, so they are responsible for routing the data, encapsulating the segments, decapsulating the frames when they get it. So they get all of that. Routers run OSPF to find out which networks are attached to which routers, things like that. Okay. So that's where at the network layer, you put the data in there. The IP package goes into a frame. The frame goes into the media, and the media goes that is sent to the destination. Then the media access control, the NIC will grab the data. He's the one who accesses the media, the wire. Grabs the data and then gets to the frame, opens up the frame, then gives it to him. Pulls the packet out at the the network layer, and at the network layer, you pull the you open up the packet, you pull the segment out, and then you open up the segment, then you get the data. And it just keeps decapsulating it up to the application layer. All right, so this is the segment, and this is the IP packet. So this whole segment, this is the data from the upper layers, layer 5, layer 7, 6, and 5. You put all the headers on it, it becomes a segment. And then this segment is placed right here, and you attach headers to it, like the IP addresses. And then this whole thing becomes an IP package. So the characteristics of an IP. Please write these 3 bullet points down to categorize IP. It's connectionless, which means it doesn't connect to the destination to see if it's there or not. You just send out data, and the data may be routed. That's why your packet may get lost, because your destination doesn't even exist. That's why we need a TTL number placed on the package, just in case that the destination is not there. So now, if it was connection oriented, we would contact the destination, and if he's not there, we don't send any data. So that would be nice, but that slows things down a little bit. IP doesn't do that. He just sends out data, and if you're not there, your packet is going to die because the TTL number will reach 0. Best effort, they will try their best to get to the destination. They reroute your packets as much as they can to get it as quickly as possible to the destination, but it may not get there, so it's not guaranteed. Media independent, meaning it could be on a copper wire, coax, and even on a fiber, right? Doesn't matter what type of wires you have. All right, so these are just analogies of what I just talked about. Connection and connection-oriented, the best effort, and the media independent. In the header packets, then you have the IP addresses, the TTL numbers, and a whole bunch of other. Here's a picture of all the different types of labels that are placed on the data. Here's your data. Here's your destination IP address, which you get from the DNS server, the source IP address. Here's the TTL number. Every time you go through a router or hop, this is decremented. If it reaches 0, then the whole packet is thrown out. This is to indicate that this is an IPv4, had checksum to check out the data, and so on. This is indicate version 4, and so on. Okay? So take a picture of this, screenshot,